I start again. So my name is Alfredo Ortega. He is Oren Isacson. We're going to talk about exploiting digital cameras. There you go. So, we're going to talk about how to script digital cameras, basically. How we reverse this script. This will not be an exploitation at low level. This will be a high level exploitation. We actually are writing interpreted language present in almost all PowerShot digital cameras. We're going to talk about what we can do with this and what are the security consequences of it. Okay, let's start with the basics. Modern digital cameras, I'm sure you are aware, are in fact powerful computers. They almost all have a ARM processor and a lot of memory, and they are really fast computers. They are. We have the digital cameras that we are studying doesn't have a complete memory management unit. It has a memory protection unit, so it really can run a secure operative system, but it runs an operative system nevertheless. Canon digital cameras use Dryos. It is an operative system built by Canon, and well, that's about it. We have complete computers. Of course, we are not the first that research into exploiting digital cameras. In fact, there is a huge project called CHDKey that is it has a few years already, and they're very incredible guys. They build custom firmware for Canon digital cameras. They enhance functionality, but this really can be used to attack a camera, because we can see here, this is the main problem that this approach. For this modification to work, you must download a firmware modification inside the memory card, but the memory card must be locked before the firmware can be executed. So this is not really a good way to exploit, to take over a digital camera, because you have to physically access the memory card and switch the login. And also there are other requirements like a special file system. They need FAT16, only working FAT16. So this is a great modification, but really can be used to attack a camera. That is why this project is in fact very secure. We want to see if there is another way. Okay.
So we first try to run our code exploiting the image parsers inside the camera. This way, if we could find a bug in the image parsers and write an exploit for it, we could take control of the camera as the user is trying to see an invalid image in the camera's playback mode. The ARM processor jumps to an exception handler when it tries to read or write an invalid memory address. So what we did is write in an exception handler to try to find the bugs, find bugs when passing the parsers. We did find some bugs, but before writing an exploit for them, or trying to write an exploit, we found another way that is better. The bad thing about writing an exploit for the image parsers are that this is binary, and function offsets change from camera model to model. So it would probably be very difficult to write an exploit that works in a lot of models. We found this other method, that is the interpreter and the script, when we analyzed the firmware of one camera. We used IDA Pro and we can see a lot of interesting strings. These strings show that there is a plain text parser inside the camera. This parser is composed of two parts. One is the YAG, that is yet another compiler, and the other is Flex, that is a lexical scanner. Well, we later found that, I was saying, we find this parser, and this parser are commonly found in interpreters and compilers. We assumed it was an interpreter as it makes more sense inside the camera. We later found we were not the first one to find this interpreter, but there is no public information on how to write a script for the cameras or any information on the syntax or semantics of this language. And it is very difficult to just guess how to write a script for this language, because any error causes the camera to simply shut down, and there are no error message that say why the script is invalid.
Okay. So we found a word language activated inside every camera, and so we have to reverse a complete language. Now that is a little difficult. What we have how to execute the language. We have what are the requirements that a memory card has to execute a script. They have a little file when the script is placed and some tags inside the boot sector. But most importantly, it doesn't require anything more than that. It doesn't require the memory card to be locked. It doesn't require a special file system. So if you have a malware running in your computer and you insert a memory card, this malware can inject code in your camera, because you don't only have to remove the memory card, insert in your camera without doing anything else, and it will execute. So I say, well, that is very useful. But we need to reverse an interpreter. It's not an instruction on an algorithm, but a complete language. So let's start from the beginning. What are the structure of this interpreter? Well, it's a very standard interpreter. We have a grammatical parser here, a lexical parser is Lex and YAG. By the way, Lex was built with an idea of Donald Knuth, and Lex was built by Eric Schmidt, CEO of Google, and YAG was built by Donald Knuth. They are software, open source software that have more than 30 years old, but they are like the standards of build interpreters. Basically, you have the script here, and the tokenizer, the Lex parser, will start read character by character and produce tokens. These tokens can be while, print, variables names. They are basically tokens for any language. They are fed to the grammatical parser, and the grammatical parser can either produce code, so you have a compiler, or interpret or execute functions, execute a program, and you have an interpreter. That's all. In this case, of course, the camera inside has an interpreter, not a compiler. It will be very crazy. You have a compiler in your camera, but you have an interpreter. So this is the function that does the parsing. This is a very complex function. We have the string here is syntax error. The string that we found, and we see that this is an interpreter, in fact. Here we have a call to the lexical analyzer, and here's this little basic block here. So we're going to start with trying to do what tokens made our language. So we don't know even what language is or any of the rules. So this is a tokenizer. It's very complex, as you can see. And in fact, it's a huge case. This is a case statement, one for each token. And the tokenizer, in fact, is a table-based regular expression. Basically, is a regular expression parser. That's why we really can't find the individual tokens in memory. The tokens are coded inside a huge table that this table is fed to a state machine, and the state machine recognizes tokens. So we couldn't find any tokens in looking at the firmware or looking at the memory. We have to reverse the regular expression parser. Here is a portion of the parser. The parser is open source, so we know that we have the source code, but we don't have the tables. One idea that we have is to emulate this in a computer. Just pick up the table from memory and emulate. There is not a single table. There is a lot of tables in a Lex parser. In this diagram, we look in the memory here. This is a table, in fact. We implemented the table back to C code and just recompile a standard Lex parser and then brute force it. There is. So we're gonna do a demonstration. We're gonna run a demonstration of this brute forcing process here. This, of course, is running in my laptop because only we we pick up the tables. Here is, yeah, we are brute forcing every character. When you say success here is that a token was successfully parsed or accepted for the tokenizer. So every number is a valid token because numbers are tokens too. Now we're going to start parsing the operators. So this is our valid operator for this language. Letters are also valid tokens because we can do variables, and we have here we have a token that is function. Function is a valid token too, so we have a function. We have if with several case, if with uppercase, lowercase. We have here sub. Sub is another token. We are accepting every token of this language, so we run this for a while, and we have this. We have a lot of tokens belong to this language, so maybe it's familiar to you. These are basic tokens, so this language is basic. Now we know that every camera has a basic interpreter inside, but we don't have the grammatical structure. It can be millions of variations of basics, so for that we should build an emulator. Now Oren will talk.
Well, as Alfredo was saying, having the tokens was not enough. Even if we tried some basic scripts, very simple basic scripts, they appeared invalid. So we had to emulate the original firmware on an emulator. We use QEMU that has the capability to emulate an ARM processor, but can't emulate the whole camera. So we couldn't use it to boot the original firmware and try to parse a script with it. Instead, what we did is capture the state of the machine, of the camera, as it was parsing a script, that is, capture all the registers and all the memory, and dump it to the memory card. And then take that information and resume the execution inside our emulator. To do this, we couldn't just set a breakpoint inside the interpreter and take control, because we are not sure that that's even possible. We had to use the exception handlers. What we did is force the script interpreter to raise an exception as it was beginning to parse a script. We can see from the source code of the Flex scanner that it tries to access an array with a value that is inside a static variable, and we change that value, and then as the processor tried to access that value, it crashed, and then we could dump all the state. To know which memory regions we need to dump, we just use the memory protection unit. Inside this unit, there are registers that define the valid memory regions, and we only need two regions: the main memory and the ROM. To control the execution of the emulator, we used the integrate GDB server, and also the integration of GDB with Python. This way, we could write a Python script and control the execution from it. This Python script can set breakpoints, modify the registers, and control all aspects of the emulator. Well, we need to make some changes to the original firmware because we couldn't allow it to call the operating system because it wouldn't work. It would try to access some hardware registers that weren't emulated. So we changed the read function so we could feed the emulator or script, and we did in a way that it read one character at the time. And this way, when the interpreter found an error as it was parsing the script, we could find exactly at which point the error was found. Well, this is the general way that we found out about the syntax. We tried a script and found out the location of the error, and then we changed it until no error was found. These are three scripts. The last one is valid, syntactically valid, but it doesn't do anything. The second slide shows that if you try to call a script, a function, outside the body of another function, that's an error. You can only call function from the body of other function. So this way we realized that there must be one function that's the entry point. I'm going to show you now the emulator as it's running. The emulator is already running. I'm just going to run the Python script. You can see here in blue the script that is about to be fed. The emulator read all the script one character at a time and found out exactly where the error is found. In this case, var isn't defined. In this second demo, I'm going to show a valid script that hasn't the entry point. So we arrived to a breakpoint that doesn't lead to code execution. This way, we later found about the entry point. This is the third demo that with the initialize function, that's the entry point. This script is totally valid, and we arrived to a breakpoint that shows that code is about to be executed. This is a complete valid script that prints hello world to the camera screen. You can see that there are a lot of predefined functions inside the camera. Alfredo is going to talk about it.
Okay, at this time we have the grammatical structure of the language, we have the tokens, but the language also have a lot of functions that we can call. In fact, this is wrong. There are 5,000 functions, sorry, 500, inside a common Canon camera, governing everything from the sensors, little motors, accelerometers, CCD, absolutely everything you can access from this language. In fact, you can access the main memory of the kernel using poke and pick instructions because it's basic, like Commodore 64 basic. We started to build a document and a user guide of this language. Is here we are going to put it online after this. We are documenting all the functions. We don't have all, of course, because there are 500, but we have some of them. There are very interesting things about this language. For example, there are functions you read about the kernel process memory here. You can see this is the equivalent of the top Unix command inside a camera. So how many processes you think a camera can have? Well, it can have hundreds of about 70 processes inside a Canon camera. All these processes governing from the buttons to the display, for keeping the CCD warm. It's a very complete operating system inside this camera. I'm going to publish this document in short, so everybody can start building scripts. Okay, what we can do with this language? Well, because it's difficult to do something with the camera, but you can do some stuff, like we're going to show now. For example, you can, the old school that we showed at the beginning. Okay, here is going to show. This is the little school that we showed at the beginning. This is not new, but this is. We're going to show this script in a lot of cameras, and it should work because it's basic. It's not accessing any low-level system. Okay, you have, this is a cheaper camera. This is a 470 Canon. The first one was a G10, one of the high-end cameras, but the script works perfectly. You want to test in your camera, Oren? Well, it will work in every PowerShot camera. Let's see. Let's see if it works. Show it. Okay. Well, work perfectly. We don't have any special code to choose between cameras. It's the same code. It works in every camera. Okay. So what else we can do with this script? Well, of course, we can make pictures appear. We can put fake picture in the camera, for example. Well, just a minute, please. We're going to show a demonstration about, well, you can put any kind of image inside the camera. For example, we're going to erase every picture inside this memory card. Okay, it's ready. So we're going to show that there is no picture in there. It's like a magic trick. There's no picture there, so we're gonna launch the exploit. Okay, launch it. There is exploit deploy, and then we will turn on the camera again. We know there is a picture of General Perón there. Of course, this picture didn't exist before, but we put it there, or exploit just made a picture appear. So this is not so dangerous until you start putting pictures of illegal things in the cameras, and then you have to explain to police that your camera has a virus. But we have a more serious exploit here. It's about, maybe you have heard.
This exploit is very new. It's the linking exploit that was made public just a weeks ago. I have a SD without the files that exploit this bug, but there is a script for the camera that will launch this exploit.
Okay, let's try. We don't have space for the USBs here. First, we're gonna show the memory card. Nothing happened here, but this is the script. You can see it here. This is the script that launched the link exploit. It just creates a lot of links inside the memory card. It doesn't have eject, so we're gonna eject it anyway. We're gonna run text exploit in any camera. In fact, can be anyone. We're gonna launch this one the cheapest. Let's see if this works, because if it doesn't work, we have a video, so you can believe it. Sorry. There is. You say exploit ready, and then you just remove the memory card. You see it is work because we never tested this really. And whoops. Well, code execution. Well, this is the famous link exploit that when you execute, when you see a memory card, it used for a. I'm sorry.
Yeah. Sorry, this wasn't supposed to be this way because we forgot to reset the Explorer process. The problem with this is that once we showed the empty memory card, the shortcuts were still there. So I'm going to show it after resetting the Explorer process.
Okay. Well, okay, we got a video that we're gonna upload that it works. Well, in fact, kind of work it, but not like we wanted to do. This is a real exploit that we basically are just copying a file in the memory card, and when you just saw the file, it will execute code like this one, like this showing here. Of course, it can execute any kind of code. And well, that's countermeasures.
It's about countermeasures. You have to be ready to be sure that there are no files with these extensions, as these are necessary to launch CHDK or the script. So if there are not 8 of these files in your memory card, you are safe from this. Canon cameras use picture transfer protocol. And that means when the computer is connected to the camera through the USB cable, the computer can't read the root directory of the memory card. So the good news is that you can get infected through the USB cable, but the bad thing is that no antivirus can scan the whole memory card when it's connected by the USB cable to the camera.
Well, so that's all. We have a language that we found inside every PowerShot camera. We documented it. We're gonna put it online. So if you have a digital camera, now you have a general purpose computer that you can use to program in BASIC. It will run in every PowerShot. No, I don't know it's everyone, but every PowerShot camera that we test. So that's it. Thank you very much.